Welcome all. My name is Dr. G. Brinda from the Department of Computer Science and Engineering, St. Joseph College of Engineering, OMR. Today's my topic is 4-bit ripple carry adder. This topic is under the subject DPLD, that is all digital related subjects. This topic will be there. This is a type of adder. So this is a 4-bit triple carry adder. So 4-bit triple carry adder means addition of 2 bits, that is 2 numbers. Addition of 2 numbers. It comes under the concept of adders. So that is basics of adder is of half adder, full adder, then it is of a ripple carry adder. So half adder is addition of 2 bits and full adder is addition of 3 bits. So these are the basic adders, and advance of this adders is of a 4-bit triple carry adder. So under 4-bit triple carry adder we are adding 2 numbers. Each number has 4 bits in it. Therefore A is one number, B is other number, A has 4 bits and B has 4 bits. So 4 bits A2, A1, A3, A2, A1 and A0. Similarly B3, B2, B1 and B0. These are 2 numbers. So this is a concept of digital, therefore addition of zeros and ones. 4 bits represents a number which has the combinations of ones and zeros. Okay, so any number can be converted to a digital format. Those will be coming under the concept of basic digital. So after the digital concepts, so this is whatever the circuit, that is design of a circuit, 4-bit triple carry circuit is nothing but it should add 2 numbers which has the combinations of all ones and zeros. Okay, so whatever the combination it may be, the circuit should perform the addition. So that combination will be of one number is of 4-bit, other number is of other 4-bit. So for it is a generalized structure A3, A2, A1, A0. Similarly B3, B2, B1, B0. Okay, so whatever the combinations, for example we can take 1001, 1101, whatever the combination it may be, the circuit should perform the addition. Okay, so whenever we are adding these 2 numbers, so 1 plus 1, so we always addition will be from the last bit. So here last bit is said to be of LSB and first bit is said to be of a MSB. Last is LSB, first bit is MSB. So addition always from the last end, LSB. So when adding these 2 numbers 1 plus 1, your addition of 1 plus 1 is addition of 1 plus 1 is 1 0, which is equivalent to similar with typically, so to general max 1 plus 1 is nothing but 2, right? 2 or binary representation is 1 0. So that is what is written over here. So in this 0 will play a sum and 1 will play a carry. Okay, so when you add these 2 numbers, same way answer will be 1 0. Whenever adding 1 plus 1, answer will be 1 0. So in that 1 0, 0 is considered as sum and 1 is considered as carry, which is carried forward to the previous bit. Similarly, so when you are adding over here, this of 3 bit now. So 1 plus 0 plus 0, so which will give you the resultant answer 1. Similarly, so no carry forward over here because the 1 plus 0 is 1, 1 plus 0 is 1, or 1 again. So it is of a 1 bit and therefore only 1 bit, therefore sum is there, no carry is there, therefore carry place is empty. So empty can be taken it as 0 also. Okay, so which means that 1 can be written as 0 1 or 1, both are same, no? So say such a way that so 1 over here and carry over here 0. Okay, so carry 0 over there, therefore now adding once again adding 3 bits, 0 plus 1, so therefore 1 over here and carry no carry, therefore 0 once again over here, and over here next bit 0 plus 1 plus 1. Okay, so 0 plus 1 is, that is 0 plus 1 plus 1. So adding these 2 numbers will give you the answer to 1. So after that adding with that 1 plus 1, 1 0. So as I said earlier, 1 plus 1 is 2, 2 or a binary number is 1 0, therefore 0 over here, 1 over here. There is no previous bits over there, therefore I am writing the carry over here itself. Therefore these things are considered as sum and this is considered as 0. These are also carries, therefore this will be labeled as C, this is also C, and this will be labeled as sum. This is one example. Similarly, for generalizing this, because whatever the combinations of ones and zeros, the circuit should perform the addition operation, and therefore when you are taking a generalized structure, I am taking this bit as A0, this bit as A1, this bit as A2, this bit as A3. Similarly, B0, B1, B2 and B3. When you add these two, you will be resultant answer will be this one S. Therefore, I am taking it as S0 and it will be resulting with a carry. Therefore, this carry C1 I am considering. Okay, C0, I will tell you where to apply C0. So, first take your C1 over there. So, adding these 3 bits, for example these 3, when you add these 3 bits, the resultant answer is this and this no. So, this will be S1 and this will be C2. Similarly, next bits will be of adding these 3, next 3. So, this is sum and this is carry. Therefore, I am taking my sum to be of S2 and carry to be of C3. Similarly, adding these 3, sum will be S3, these two concepts, no. So, sum will be S3 and C4. Okay. So, whatever the combination of ones and zeros, 4-bit combination if you take, your resultant answer will be of this structure, right. Okay. So, whatever the combinations it can be. Okay. So, while seeing to this, so last adding 2 bits, before bits adding 3 bits. So, this is again 3 bits, this is again 3 bits. Okay. So, which is nothing but addition of 2 bits, as I said earlier, you can use half adder circuit. Addition of 3 bits, you can use full adder circuit. Similarly, addition of 3 bits, you can use full adder. This is also once again full adder. So, for designing the 4-bit triple carry adder, you should use 1 half adder and 3 full adders. To make it to be of a generalized thing, we can make this 2-bit also to be of a 3-bit by adding 0 over here. Okay. That is, so in this, by adding 0 over here, this 2-bit can also be considered as 3-bit. So, starting, so whenever 0 is equivalent, whenever empty spaces, we can add zeros, you can use zeros, right, and therefore, if you add 0 over here, this 2-bit can be made to be of a 3-bit. Okay. So, therefore, here also you can use one more full adder. So, 4 full adders together will be used for construction of a 4-bit triple carry adder. Therefore, so this 0 over here is specified to be of C0, where C0 is always equal to 0 for addition. C0 is always considered as 0 for addition. Now, coming into a circuit, so I said this is one full adder, this is other full adder, this is other full adder. So, 4 full adders. So, full adder circuit, we are not going to make a full adder circuit. Full adder circuit is a pre-designed circuit, and therefore, I am going to represent it in the form of a block format. So, block format is one full adder. Okay. So, full adder concept, after completing this, I will explain you once again the full adder concept. So, this is one full adder. So, 4 full adders you need, no. Therefore, this is other full adder and third full adder, and this is fourth full adder. So, how will you connect all these full adders? So, full adders is nothing but addition of 3 bits. So, it needs 3 bit as a input. Okay. Therefore, 1 input, 2 input, other input I am taking it over here, because C0 is for the last LSB full adder, C0 is my 1 input, where C0 is considered as 0 for addition operation, and therefore, this I am taking it over here as C0, which is always equal to 0 for addition. Okay. So, this is C0. So, my last full adder, this is my last full adder, right. So, for last full adder, my inputs are C0, B0, sorry, C0, A0, B0. My output will be S0 and C1, right, and therefore, I am taking it here as A naught, B naught, C naught. These are 3 inputs. Output will be my S naught and C1 is my other output. When you add these 3 numbers, you will be resulting with the sum and carry, no. So, this carry is taken as the input of the next full adder, and therefore, the carry of this will be considered as the input of the next full adder. This is C1. There I label it as C1, therefore, it is C1. So, this is my first full adder. Same way, repetition for your second full adder. Second full adder, my inputs are C1, A1, B1 and my outputs will be S1 and C2, right. And therefore, for the second full adder, C1 is already there, which comes as the output of your first full adder, and my inputs are A1 and B1. My outputs are S1 and C2, where C2 acts as the input of the third full adder, and therefore, C2 is over here. Similarly, for your third full adder, my inputs are C2, A2, B2. Outputs are S2 and C3. Therefore, C2 is already over here. Therefore, A2, B2. Output will be my S2 and C3. S2 and C3. C3 is obtained by adding these 3 bits. Okay. Now, for the fourth full adder, my inputs are C3, A3, B3. Outputs are S3 and C4. Therefore, C3 is already there. A3, B3. My outputs are S3 and C4. No further full adders, therefore, C4 I am taking it as the output. Therefore, my outputs are S0, S1, S2, S3 and C4. These are my outputs. So, this is my addition circuit where 4-bit triple carry adder is a MSI device, medium scale integration device, MSI medium scale integration device. So, which is nothing but medium scale integration. Under that you have a small scale integration. So, this full adder circuit, this is one circuit which is been devised inside the full adder thing. Okay. So, 4-bit triple carry adder thing, and therefore, this is one circuit, this is other circuit, this is other circuit and this is other circuit. All the circuits are molded inside one chip, IC chip. So, that IC chip which has inputs, set of pins in the inputs and same way outputs. So, you will be having your supply and ground. So, this is said to be of a MSI device. So, this is one example of MSI device. Okay. So, inside that integrated chip, this entire circuit will be fabricated inside it. Okay. So, for that your inputs are A0, B0, A1, A2, A1, B1, A2, B2, A3, B3, and C0 is also acting as an input, which is created by you for your 4-bit triple carry adder, where C0 is always considered as 0 for addition. 0 for addition. So, this circuit will perform only addition. So, for this outputs are S0, S1, S2, S3 and C4. Okay. So, when you use this chip, when you give these inputs 1001 for A, 1101 for B, you will be getting the resultant answer of this. You can't able to see all these answers, you can able to see the resultant answer of this. This is for your addition. Next, subtraction. So, addition and subtraction are both are indulged components, right. So, which means that in digital, subtraction is not is done by actual subtraction. So, subtraction concept is being carried out in digital in the form of complementing. In the form of complementing. Complementing is nothing but A minus B is your subtraction, right, where this A minus B can written as A plus of minus B. That is, by negating the B value after adding with A will give you the resultant answer as subtraction, A minus B. So, for bringing out this format, they are keeping your A as such, and B, they are converting this B to be of a minus B, which is nothing but conversion of to B to minus B is nothing but taking 2's complement of B. 2's complement of B will be equivalent to minus B. Okay. So, 2's complement of B will be equivalent to minus B. Therefore, if you are taking A minus B, the same concept will be written as A as such. There won't be any changes in the A because A is a positive number. Therefore, A3, A2, A1, A0 is as such, and only B, they are considering it as minus B. Minus B is nothing but, I said already, it is a 2's complement of B. Okay. So, which is nothing but 2's complement of B is nothing but 2's complement of B is nothing but 1's complement of B plus 1, adding 1 to the LSB is said to be of a 2's complement of B. 1's complement is nothing but negation of B, negation of B plus 1. Negation of B is nothing but B bar. B is equal to B bar, this plus 1. B is equal to B bar. For example, if my B is equal to 1101, B bar is equal to 0010. In place of 1, 0 should be there. In place of 0, 1 should be there. This is said to be of a negation concept, which is nothing but 1's complement of B. Okay, this is an example. Okay, therefore, for minus B, you are supposed to represent it as B bar, B bar 3, B bar 2, B 1 bar, B naught bar. Okay, and this adding 1 to the last bit, and therefore 1 can be added over here. This entire thing represents minus B. This entire thing represents minus B. So, after converting this B concept into this 2's complement, normal addition will be performed. Okay. So, which means that adding these two. So, now here 1 is there, therefore 3 bits over here, therefore your resultant answer will be S0 and C1. Normal addition value only will be performed, plus 1 no. So, normal addition value will be performed. So, S0, C0. Similarly, C1, A1, B1 dash will give you S1 and C2. Similarly, C2, A2, B2 dash will give you S2, C3. Similarly, C3, B3, B dash 3 will give you S3 and C4, which is equivalent to, that is, operation over here is done as normal addition, but the resultant answer will be whatever the answer we get, that is direct subtraction la A minus B in answer vandhudo, same answer will be reflected over here. Same. In this methodology also you will be obtaining same answer as such of your A minus B. Okay. So, which means that without directly, because in subtraction, if you are subtracting 0 minus 1, from 0 1 cannot be subtracted. Therefore, you need to get a borrow. So, if you get a borrow, so borrow here it is numbers are only zeros and ones, no, and therefore borrow can be borrowed only with 1 bit. So, if you get a borrow, this 0 will become 1 0. Okay. So, if we get a borrow of 1, this 0 will become 1 0. 1 0 value will be equivalent to 2. Therefore, 2 minus 1 will be equal to 1. Okay. Therefore, for 0 minus 1, if you are getting a borrow, that is, this 0 will occupy 1 memory space. If you are getting a borrow, it will occupy 2 memory spaces. Okay. Then from 1 0, if you subtract, the answer will be equal to 1. So, difference is 1 and borrow is also equal to 1, okay, if it is for a single bit. If it is for a multiple bit, that is if you are getting a if you are taking a number of this, if you are taking a number of this, okay, then if in case, so that is 1 0 0 minus 1 1. So, in this from 0, from last LSB you are subtracting. So, from LSB 0 minus 1 you can't subtract. So, you need to take a borrow. So, if you are taking a borrow, it will be getting a borrow from the previous bit, but previous bit is also 0. Therefore, this 0 will request a borrow from the its previous bit. So, its previous bit is 1. So, from here if you take a borrow, this if it giving a borrow, then it will become 0 and this 1 0 will become 1 0 now. So, after it is receiving a borrow from this, it will give one borrow of over there, and therefore, when it is giving a borrow of that, this 1 0 will become 0 1 and this 0 will become 1 0, okay. So, which means that this 0 1 is nothing but 1. So, this 0 1 can be written as 1. So, which means that while getting a borrow, it occupies 2 memory spaces. For giving a borrow, it occupies 1 memory space. So, the memory allocation for whatever the circuit designing, it will be of quite complex in this subtraction concept of digital, and therefore, in order to make this concept to be of easier, while they are making this subtraction operation, they are performing this subtraction operation in form of addition itself. So, in form of addition, if you subtract a concept, that is in order to convert your subtraction in form of addition, they are taking the 2's complement of the addition. Therefore, that is subtraction. So, which means that while getting a negative values, if you are taking a 2's complement and if you add it as a normal addition procedure, then you will be getting the same similar answer. Exact direct subtract பண்றப்ப என்ன answer வந்ததோ same answer you will be getting in this concept also. Therefore, subtraction concept is not there in addition. But while seeing it in addition, whenever you are adding 2 bit or 3 bit, resultant answer will be 2 bit. It is a standard for whatever the combinations. Resultant answer will be 2 bit. So, memory allocation is neat, no? So, in subtraction it is not so. For few values you are supposed to give 2 bits, for few values you are supposed to give 1 bit. So, for all those sorts of confusions, this subtraction has been performed in digital in form of addition, and therefore, this complementing procedure came into a role. So, with the help of this complementing property, the subtraction can be performed in terms of addition itself. So, that is what this strategy A minus B. That is what strategy A minus B. So, for A minus B also everything is same, but that is only thing is input, instead of in minus subtracting minus B, you are considering this as A plus of minus B. A plus of minus B. So, minus B is a negation number. So, for negation number, minus B can be represented as 2's complement of B, where 2's complement is 1's complement of B plus 1. So, this is what the structure over there. So, in this, for this structure, so if you see that is for this structure, if you see this, what is the difference between this and this? This is for A plus B, this is for A minus B, okay. So, if you see this general structure, every concept is same, right? See, A remains the same as such, and carry also remains the same, only the C naught is getting varied. For addition, C naught you are considered it as to be 0, no? For C naught you are considered it as to be 0. But over here, so if you take this last 3 bits, is already it is of a 3 bit, okay. Therefore, so this A naught, B naught dash plus 1, this 1 where it comes? By 2's complementing procedure of B, this 1 appears, and therefore, this 1 can be considered as C naught over here. It is already of 3 bit, okay. Therefore, full adder can be implemented for this. So, this C naught is considered as 1. So, in this generalized structure, we can say that whenever C naught value is equal to 1, the circuit will perform subtraction operation. Whenever C naught is equal to 0, the circuit will perform addition operation. This is the concept, and apart from C naught, this B naught is that is B values, B variable is getting varied. Here B variable is same as such, but here B variable is complement of B. Okay. So, rest apart from these two logics, rest all concepts are same, no. So, typical. So, in the same structure, this structure with a slight modification, this circuit can be utilized for subtraction. So, what are the changes? C naught should be equal to 1. Whenever C naught is equal to 1, the circuit will decide, that is the circuit will give the subtracted operation. Okay. So, a B naught it should be changed as bar. So, similarly B2 bar and B3 bar, but on a we have the inputs as B only. How this bar will be obtained? By adding NOT gate, So, this is B naught. Similarly B1, similarly B1, similarly B2, similarly B3. Okay. So, for this output of NOT gate is B3 bar, this is B2 bar, this is B1 bar, this is B0 bar. Okay. Therefore, my inputs are A0, B1, B2, B3. So, by using this subtractor circuit, that is NOT gate circuit, this circuit will perform the subtraction operation. So, I think for addition and subtraction I have changed only this C0 and this B0 entries, right. Rest all concept is similar for addition and subtraction. Okay. So, two different circuit, but subtraction is also being done in the way of addition, right, and therefore, these two circuits can be merged into a single circuit, right. So, for merging of those two concepts, they implementing the one more concept called as M, where M stands for mode of operation. M stands for mode of operation. This mode of operation, equation for mode of operation M is nothing but, what is the difference between your addition and subtraction? For addition, C0 value is 0, for subtraction C0 value is equal to 1, and for addition for both addition and subtraction A value is the same, but B value for addition it is B itself, for subtraction it is B bar. This is the difference, no, and therefore, so B value and C0 value it is getting varied, and therefore, combination of those two C0 XOR B is the equation of mode select. C0 XOR B is the equation of mode of operation, that is mode select. Okay. So, we will check whether these concepts is getting tallied with this equation. Therefore, that is M is equal to C0 XOR B, no. So, now consider your C0 is equal to 0. When C0 is equal to 0, what should be the B? B should be in the form of B itself, no, which means that B eppadi ulla kudukriyo same way it should be reflect as output, same B oda value B ave varanum. So, if B value is 0, this expression should give 0 itself. If B value is 1, expression should give 1 itself. This is the logic, no. So, now when C0 is equal to 0, okay. So, when C0 is equal to 0, let us check whether this expression is getting satisfied, C0 plus B. So, I am considering my C0 is 0 because it is a addition, we are checking for addition operation. So, C0 is equal to 0. So, I am fixing that value, and B value, B value first I am considering it to be 0, first I am considering it to be 0. So, sorry, XOR no, first I am considering it to be 0. So, 0 XOR 0, what is my XOR logic? What is my XOR logic? A XOR B is equal to A bar B plus A B bar, no, which is equivalent to A bar B plus A B bar. Same way C naught XOR B is equal to C naught bar B plus C naught B bar, right. So, same way if we implement it over here, what is my C naught value? It is 0, okay. Therefore, in this expression if we implement C naught is 0, therefore C naught bar is nothing but 1 dot. What is my B? B I am considering it as 0, therefore 0 itself, plus what is my C naught? 0, so 0 dot B bar I am considering it as 0, therefore 1, okay. That is B is 0, B bar is equal to its complement, for 0's complement is 1, 1's complement is 1, okay. So, which is nothing but 1 dot 0 plus 0 dot 1, so which is nothing but 1 dot 0 is 0, 0 dot 1 is 0, therefore dot is nothing but AND operator, plus is nothing but OR operator. So, here that is this plus is addition, so this dot is nothing but AND operator. So, 1 dot 0 is 0, 0 dot 1 is 0, 0 plus 0 is equal to 0. We are considering B as 0, we are getting this expression output is also 0, therefore, whenever C is equal to 0, B should enter B itself, okay. Therefore, this. Similarly, whenever my B is equal to 1, same for C equal to 0, whenever by me B is equal to 1, M is equal to C naught XOR B, which is equal to C naught bar B plus C naught B bar. This is my expansion of this expression, and therefore, when you take this, C naught value is 0, C naught bar therefore 1 dot B value is 1, therefore 1, plus C naught value is 0, therefore 0 dot B bar, B value is 1, therefore B bar, therefore 0. 1 dot 1 is equal to 1 plus 0 dot 0 is equal to 0. 1 plus 0 is equal to 1. So, whenever my C naught is equal to 0, B value is 1, my in the expression output is also equal to 1, which means that whenever my C naught is equal to 0, B will enter B itself. B will enter B itself for this expression, okay. Similarly, same concept should be worked out for your C is equal to 1, right. So, C is equal to, for addition we have checked this expression works. Similarly, when C is equal to 1, C is equal to 1 is nothing but subtraction operation. So, subtraction operation nothing but B should enter as B bar, B should enter as B bar, right, and therefore, so in the same expression M is equal to C naught XOR B, which is equivalent to C naught bar B plus C naught B bar. So, in this expression if my C is equal to 1, first I am considering C B is equal to 0, for both the concepts it will work, right. So, B is equal to 0 and B is equal to 1. First we will go with B is equal to 0. So, C naught bar, C is equal to 1, therefore, C naught bar is equal to 0 dot B is equal to 0 plus C naught is equal to 1, B bar, B is 1, sorry, B is 0, therefore, first we will see this, B is 0, B bar is equal to 1, therefore, now 0 dot 0 is equal to 0 plus 1 dot 1 is equal to 1, which will give you 1, 0 plus 1 is 1. So, which means that we are consider B value to be of 0, but as per this expression we are getting the output is equal to 1. So, which is nothing but B bar, okay. So, for C is equal to 1, B should enter as B bar. So, now this logic is works. Similarly, for B is equal to 1, considering B is equal to 1, M is equal to C naught XOR B, M is equal to C naught XOR B. So, which is equivalent to C naught bar B plus C naught B bar, okay. So, in this which is equal to C naught is equal to 1. Sorry, this is C naught bar. C naught we are considered as 1, therefore it is 0. Dot B we are considered to be 1, therefore plus C naught is 1. B bar, B is equal to 1, therefore B bar is equal to 0, which is nothing but 0 dot 1 is 0 plus 1 dot 0 is equal to 0. So, which gives 0 plus 0 is equal to 0. So, whenever C is equal to 1, if we consider B is equal to 1, we are getting this expression answer as 0, which is nothing but B bar. Okay. Therefore, this expression works. So, in the same circuit, what you are supposed to modify? C naught is over here. What you are supposed to modify? You are supposed to introduce this M concept, where M is equal to C naught XOR B. Okay. So, C naught XOR B. So, which is nothing but XOR gate. So, you are supposed to go with the XOR gate. So, for all B's should be given via this XOR gate. So, B naught over here. Okay. That is, one input is C naught, other input is B, that is C naught and B. Okay. So, one input is C naught, other input is B. So, B I am taking here B naught, B1, B2, B3, therefore B naught. So, it should go via the XOR gate. Okay. So, this should be my mode select. Okay. So, whenever my M is 0, whatever the B value, 0 na, it will go inside as 0, it will 1 na, it will go inside as 1. Whenever my M is equal to 0, which means that addition operation, for addition operation. And whenever my M is equal to 1, this M, when M is equal to 1, then C naught will be equal to, so or else you can change this as, this is C naught, no, this is M. Okay. Same, that is, this end is M, this end is C naught. Okay. So, whenever my M is equal to 1, C naught is also equal to 1, and here C naught will be equal to 1, and therefore, here B naught will be, it will be, that is via this XOR gate, it will be entering it as B naught bar for your M is equal to 1, which is nothing but subtraction operation. Same, this concept should be implemented for all the B's. Therefore, all the B should be modified as with the XOR gate. So, all the B should be connected with my XOR gate. Okay. Same, this C, commonly the C should be given to all. Separate கொடுக்க கூடாது, it shouldn't be given separately. This C naught should be connected to all the circuits. Okay. Therefore, C naught should be connected to all the circuits. This is my B1, this is my B2, this is my B3, and this is my B naught. Okay. So, now this structure will give you, whenever this M value is 0, this circuit will perform addition operation. Whenever this M value is equal to 1, this circuit will perform subtraction operation. Therefore, this is said to be 4-bit ripple carry adder circuit. So, where this single circuit can be used for both addition and subtraction. Okay. So, I repeat again. So, this is a generalized concept. So, whatever it is, whenever your m value is equal to the m value, this is m value, m is nothing but mode select. So, m value may be 0 or 1. So, whenever there is m value is 0, this structure, so this B will enter as such, all the B's will enter as such, and the circuit will perform the addition operation. Therefore, S0, S1, S2, S3, C4 will be obtained. Same way, whenever my m value is equal to 1, this B will be entering it as B0 bar, B1 bar and B2 bar and B3 bar for m is equal to 1, for m is equal to 1. So, it will give you S0, S1, S2, S3, C4, where this S0, S1, S2, S3, C4 will be my difference, for my subtraction, where for 0 for addition this will be my difference, where for addition C4, S3, S2, S1 and S0 will be my sum, for addition. This is for subtraction. Okay, this is for subtraction. Thank you.